Good morning. Welcome back to our gas state and liquids. This thing today we'll finish this thing. Two small things we'll see today. There will be normally confusion between the normal boiling and standard boiling. Normal boiling means normal boiling. I am writing as NB because I am a shortcut. This thing. This is boiling at 1 atmosphere. 1 atmosphere temperature is normal boiling. Whereas standard boiling, SB, standard boiling, if you see, this is at 1 bar. What is the difference? Means slightly bar is lesser than the atmosphere, slight less. So if it for the water it is 900 degrees and 99.4 degrees like this. So always don't get confused. Normal boiling is at 1 atmosphere and standard boiling is at 1 atmosphere. And boiling, you understood everything. The vapor pressure, when it is equal to the atmospheric pressure, then it will be the temperature at which it will boils. The pressure varies means atmospheric pressure varies means the boiling will vary. Suppose if you see 1 atmosphere pressure, water boils at 100 degrees centigrade. Water at 100 degrees centigrade at 1 atmosphere. But if you see if it is some 6 atmosphere, it will be 150 degrees centigrade. So why we are talking like this? This can go on like this. At particular temperature, even if you are increasing the pressure, you cannot make as a liquid. So that was the critical point what we have discussed. For the 220 bar is the for water and some 374 degrees centigrade is the critical this thing and all. So other way of the one more way of the defining the critical temperature is suppose you take the cooker. Cooker, of course, there is a weight and the gas is going out. Suppose if it is a lid is totally closed and you are going on heating the cooker or simply boiler in a closed vessel, it will not boil. Its temperature is converting into the pressure because it is a closed vessel and there is no lid also, and so pressure is going on increasing. When compared to the steam or vapor density to the water temperature or liquid density is always high. When it is going, the temperature is increasing, the pressure is increasing, so liquid is converting into the gas, vapor pressure, but no boiling, it is going on continuous. At particular temperature and pressure, the density of the vapor is equal to the density of water. There cannot be a discrimination between the water phase and the gas phase. Till that time there will be two visible layers, water layer or the liquid layer and the gaseous layer. At that particular point, critical temperature and critical pressure point, there is no two discrimination, different layers or phases. It is only one, that is only the gas. That will be the density of the water and density of the liquid and density of the gas is equal. So that is called the critical temperature. Other way of the defining the critical temperature. Now some one or two parameters of the liquids we will see normally the surface tension. See, if you see in the pond and other things, so small flies will walk on the water surface. How it is possible? That is because of surface tension. Surface is nothing but the intermolecular forces, difference in the intermolecular forces, because intermolecular forces are all the same for the particular liquid. Whereas that is in the bulk. Suppose if you take in the beaker, in between molecule, bulk molecule is having all the four sides, intermolecular force or attractions are same. You take it to the surface point, at the topmost point. Three sides the surface pulling down. The upper portion there is nobody is there to pull up, means attractions are lesser. That's what we have seen in the gas phase also. That's why we have added P plus A by A n square by B square also. Similarly in the case of the liquid also. So the surface will be pulled down. That's why if you see the capillary, there will be a small curve in the edges. That is the reason the particles also will form, liquid particles will form as a spherical, it will form because of this surface tension only. So surface is nothing but difference in the intermolecular forces in the top. So that's all. Nothing much in there. There is a force acting per unit area that will be represented normally by gamma, and the force per unit length is the your what you call units. And surface tension decreases with increasing temperature. That is noted to be point. Because of this intermolecular forces, the surface tension is there at the top, and the temperature increases, the surface tension decreases. Another parameter what we call C is a viscosity. Viscosity is nothing but a laminar flow. You have to do it means you take it just like a flow, like a book. In the book, suppose there are some 200 pages. So flow also, a bed of the flow also you have to consider as some 200-300 layers. The bottommost layer is attached to the surface where there is a very minimum velocity, and the top layer is having a highest velocity because there is no for each layer there is a gradient. First layer it will try to move in the top, but the second fellow will object the first layer. Second layer is ready to move into the forward, and third layer is objecting, like that going on. So there is a gradient that is called velocity gradient, that is normally represented by du by dz. Dz is the where this is the distance and this is the velocity, and so force is acting directly on the area of the contact. The more the contact area, the more the force acting on this. That means the rigidity will be more. Indirectly, viscosity means rigidity of the flow. Rigidity of the flow is the correct word for this thing. So F is directly proportional to area. F is also proportional to du by dz. If you combining both the equations, F is proportional to A du by dz, and if you remove the constant, and F equal to viscosity coefficient into A into du by dz. This is viscosity coefficient. Normally viscosity is the centistrokes this thing. Viscosity coefficient the Pascal second or poise or Newton second per meter square. These are the units. And viscosity also again temperature dependent. Viscosity, the more the temperature, the lesser the viscosity. Viscosity is more useful in the case of lubrications. Higher viscosity liquids like the all you are seeing the lubricants having high viscosity and viscosity coefficient also. High viscosity coefficient, viscosity coefficient is doesn't depends on temperature, but viscosity depends on temperature. So these are the liquids and gases. We will see one small problem in the RMS velocity, and why RMS velocity is there is small confusion, though it is a simple equation. Suppose if you RMS velocity, if you want URMS, a simple equation, everybody knows that it is nothing but 3RT by m under root, but here what is the R and what is m is only the most important. So most of the time the people will get confused and they are putting the wrong values. So one small problem we'll see calculate for SO2. For SO2 at 27 degrees centigrade, what is the RMS velocity? Other velocity is one problem is means other things will be the same as the other one. So now here I am putting it root 3. R value should not be in liter atmosphere and all. It should be the joule only. That means 8.3 joule. 8.314 or whatever. 3. And T should be in Kelvin. That should be 27 degrees means 27 plus 273. It is nothing but 300 Kelvin. Now one more confusion is what is M. M is for SO2 is 2 16 32, 32 plus sulfur is 32, 32 plus 32 64. So normally people will put the 64, but it is gram. It is joule means mk. So you have to convert into the kg. Kg means it should be 10 power minus 3. That should be the equation. So it should be the kg joule, and it should be the degree Kelvin, and it should be in kg. So then you will get the correct value, that is nothing but something like 342, and the value whatever you are getting is meter per second because it is a velocity. The other, the average most probably will be the one is easy. Other things also, one is 2RT by m, another is 8 by pi RT, so nothing much to be discussed, but the only thing is R should be in joule and the M should be in kg. Okay, thank you. So tomorrow we will see some more this thing, and one more last this thing is a small this thing. So suppose two gases are there or two liquids are there. One is carbon dioxide, another is methane. Suppose these both are gases in the normal temperatures. So critical temperatures of the carbon dioxide is 31.1 degree centigrade, and this is the minus 81.9 degree centigrade. The question asked was in the some NID and all these things are also, which is having the more intermolecular forces. This is a critical temperature critical TC. So carbon dioxide is only 31, that means above 31 degree centigrade, this is will be in the gases form only, and below 31.1 only at higher particular pressure it will be in the liquid, whereas methane minus 81.9 degree centigrade also it will be in the gas form, above this gas form, whatever may be the pressure at that particular pressure. So which is having, so the first for any, not only this example, for any other example also, the more the critical temperature, the more the intermolecular forces. Suppose water you take, water is nearly 374, that is 374, if I remember correctly, 220 degrees centigrade. Water is 647 is the absolute value, minus 273, 4, 14 7 7, right. 374 degrees centigrade is the water critical temperature. And whereas if you see the other thing, means its intermolecular forces are more, and up to that point it will be in the liquid form, above that it will be in the gaseous form. Okay, thank you very much.